So, we are discussing source term linearization. So, we said if we have a general source term, that is S as a function of t, which is a nonlinear function of, could be a nonlinear function of temperature and some constants, then we have to linearize the source because our nominally linear framework would only allow a linear model to be in there for the source terms, and also having a linear dependency on the temperature on the dependent variable is much better than having a constant in there in terms of the convergence. Okay, so because of these two constraints and motivation, so we kind of linearize a source term. Okay, and there are several ways to linearize the term, whereas the recommended one is using Taylor series expansion. So, if we say we know the values of the source term at the previous iteration, so the star indicates the previous iteration values, then we expand the current value of the source term about the previous values, okay, using Taylor series. That means S would be expanded as S star plus partial S partial T star times T minus T star. Of course, you can go for higher order terms, but that is not required because we are using a linear model. Okay, so this is essentially expanding about S star or the star values, the current previous iterative values. Now, of course, if it is if you are applying for the cell P, then these would read as Tp and Tp star. Okay. Now, let us consider an example of a source term. So, an example source term is, let's say S equals 4 minus 5t cube. Okay. So, we have a cubic function for S in terms of temperature and some constant. Okay. Now, what would be, I would call this as method 1, which is using the Taylor series expansion that we have just discussed. So, what is S star here? S star would be evaluate S at the T star values, right. So, that would be 4 minus 5 T star cube, right. Okay. And what would be ds dt star or partial S partial T star? 4 minus 5 T cube, derivative of this with respect to temperature is how much? Minus 15 T square. So, that would be T star square because we are evaluating at star values at the previous values. So, now S star and ds by dt star, are they known or are they unknown? They are known because they are in terms of the T star values, which could be a guess value or which could be the latest value that we have in those locations. Okay, then if we plug in, what would be the model for S? S would be 4 minus 5 T star cube plus, or rather minus 15 T star square times T minus T star, right. That is what we have. If I plug in for S star from here and ds by dt from here, that is what we have. Okay. Right. Then we can rewrite this as S equals, we can read this S equals 4 minus 5 T star cube minus 15 T star square times T plus 15 T star cube. Okay. So, this is nothing but 4 minus 10 plus 10 T star cube, we have minus 5 T cube and plus 15 T star cube minus 15 T star square times T. Okay. So, can you identify now what is SC and what is SP from this relation? 4 plus 10 T star cube would be your SC, the constant source term, because T star cube is known, right, T star is known, and then what would be SP? Minus 15 T star square. Okay. So, SP would be this guy because what we have is SC plus SP times TP. Okay. So, we can even write it as with subscripts P everywhere if you are doing it for the cell P. Okay. So, this could even be TP, TP star NT, right. So, this is your S. So, that means what we have is we have SC equals 4 plus 10 Tp star cube and SP equals minus 15 Tp star square, okay, right. So, essentially now what we realize of course is that SC and SP depend on temperature, right. That means they depend on the temperature values at every iteration. That means they have to be updated as part of your solution loop, okay. So, we have linearized it, but SC and SP need to be updated with the iterations, right. So, essentially these have to be updated as you go along your solution loop as well, okay. Now, we had this discussion where, yeah, once you converge the T to T star, okay. So, where do we stop the iterations? That is once you reach a convergence criteria, okay. We'll come to that, we'll come to the discussion, yes. Okay. So, what if you are using a direct method? So, even if you use a direct method, this step of linearization comes before you arrive at the system of linear equations, right. So, if you are using a direct method, a completely direct method, right. So, essentially you still have to update the coefficients, right. Okay. I think now the question is interesting. Essentially you have Ax equal to B, right, where so you need to have some kind of a false iteration on this coefficients, right, because the coefficients are not correct, right, because they are depending. Essentially your direct method will only solve for a given Ax equal to B, right, but then A itself is, because of the non-linearity you have linearized it, that is why A has to be updated as part of another iteration, okay. We will come to that, we will come to that later. In a sense you have to iterate the solution for certain reasons, right. One of them is of course if you choose an iterative method, right, instead of a direct method. The other ones is if you have non-linearity, because non-linearity you cannot solve directly. So, either you have to introduce a loop, kind of an outer loop, right, where you have to update your coefficients of the A, that has to be there. We will come to that discussion little later, fine. As far as like this discussion is concerned, right now we are looking at, let us say, an iterative method, fine. Other questions? Is it clear how to linearize any source term, right? We use the Taylor series expansion. Now, we had this discussion I think few classes before, where would the coefficients be different between cells, right. In that context we said SP would be, if it is a constant it would not be, but if SP is a function of TP, then it would result in different AP for different cells, okay. You see that because TP would be different for different cells, as a result SP will come out to be different, which will in turn result in AP being different, okay. So, that will come into play. Now, of course, we have not established that well whether this linearization would give the correct solution, right, because somebody gave us 4 minus 5t cube and then we just said okay, I will use Taylor series, and I just changed the source term and then said okay, we will just convert this thing. So, we will see that little later. For now, let us also look at few other linearizations, okay, or other ways of doing this, which are not recommended of course, okay. Now, you may have, okay, the Taylor series one is basically model 1. So, let me call it as model 2. Model 2 would be, you can just say, what if I just use SC equals 4 minus 5 TP star cube, okay, and SP equals 0. You could of course do with this, right. You just dump everything in the constant and say SP is 0, okay. So, this is of course lazy person's approach, right, where you just dump in everything in the source term in the constant, okay. Now, does this work or not? Will there be a problem? What do you think might happen in this case? So, what are the of course, it will converge hopefully, right, and then you will get an answer. The only thing is that it will be slow to converge, right. So, essentially the convergence will be slow to converge, because we are not using the correct ST relation, okay. We are not using the correct ST relation. And also, what is the other disadvantage you see with this outright? By making SP equal to 0, you are losing some very good property. This Scarborough, right? Essentially, the diagonal dominance is what you are losing. Okay, so as a result, the convergence might also struggle, right? Depending on if you don't satisfy Scarborough. So essentially, the diagonal dominance could be affected. Fine. So, all right. Then, of course, there are several different ways. Another way to look at it is basically, I would say, S minus 4 5 T p star cube. So, I can say SC equals 4 minus, let us say, what we have is, we said plus 10 and minus 15, right. So, I can also have, I can say SC equals 4, okay, SC equals 4 and SP equals minus 5 Tp star square. Can I say this? Right, essentially that means my SCS equals 4 minus 5 Tp star square times Tp, right. That is my whole original model. I just say, okay, 4 is my constant, minus 5 Tp cube, I would just get minus 5 Tp star square, and then this is my SP. Can you use this model? You can use it, but only thing is that this particular curve that we are talking about, this particular line is kind of less steep than what it actually is. Okay, so essentially the first model that we had, what was the slope of the curve that we had? Minus 15 Tp star square. Okay, but so essentially this is like a tangent to the curve at Tp star, right? What will be the slope of this guy? This is only minus 5 Tp star square. So this is less steep than the original model, right? So essentially less steep than the correct slope, right? Slope at Tp star. As a result, this would also converge. Only thing is that it will again may not, so it will be again slow to converge. Okay. Fine, and it also does not account for the fall of S with T, right, correctly, right. It does not correctly account for the amount of fall of S with respect to T at Tp star. Okay. So as a result, this would also be slow to converge. Yes. Yeah. So the question is, I am just changing the source. Are we not solving different problems? I will come to that question little later. Yeah. So essentially, we will come to that in little while. Okay. So each time we change the source, are we not changing the solution also? Okay. That could also happen, right? I will come to that, which method kind of produces the correct answer when you converge. Okay. Essentially, we should be solving the same problem that is given to us, but not something else, right? Okay. Fine. So we can of course have another model where SC could be 4 plus 25 Tp star cube, and SP would be minus 20, or it should be the other way around, minus 20 Tp star square. Would this work, right? Or 20 and 25 should be exchanged, is it? What will these be? Let us see. So I have, how much is the value I had? Minus plus 10 and minus 15. So I would make it plus 20 and minus 25, right? That would be fine, right? I can come up with infinite number of ways, right? Now what would be the slope here? Slope is larger than the slope it is supposed to be, right? So this is has a steeper slope than the value at Tp star. Okay, so this is kind of acceptable, but again it might kind of slow down the convergence. Okay, so essentially the best way to look at is you should take care of from the tangent to the curve. Okay, so this also would work, but it might also kind of change the convergence rate. Now let me look at how does these graphs, yes. Essentially you are not having the correct slope of the source with the temperature. As a result, you are not capturing the correct S to T relation. So as a result, it might slow down the convergence. Okay. So this is again an observational fact, that is it's not coming from the equation as such. Okay. Yes, it need not actually give you the solution quickly, right? But of course it is good because you have now more diagonal dominance, right? You have the AP is much larger now, right? But that doesn't guarantee that you will get the solution quickly. Okay. Other questions? Yes. Yeah. So question is, will SC and SP change from cell to cell? Yes, they change, right? Do they also change from iteration to iteration? Yes, they change. Okay. Fine. Other questions? Yes. Just out of, I mean, like curiosity, that's all. It can be anything. You want to have 40 and 45? It can be anything, infinite number of ways. I just put something there which is greater than minus 15 TP star square. Yes, that is true. But then you cannot have any random numbers here because the difference has to be minus 5 star, correct? So the question is, okay, only if I am lucky the slope will be correct. So we don't have to be lucky, we can use Taylor series expansion. That's all, okay? Other questions? Yes. Right. So essentially the question goes back to the assumption we made, which is SP is less than or equal to 0. What if SP is positive, right? Or S is a positive function. Essentially whatever we are talking about, I am just calling it as source, but actually it is a sink, right? Because I have minus in there. Would you get such a problem in, like, that is physically plausible? What will be the solution for if you have a positive feedback loop? What will be the solution for positive feedback loop? So essentially you have some temperature 100, your source becomes 100 cube, right, plus, and then you have some solution. So what will be, is there a physical problem where you can get a positive source? So essentially a positive feedback loop, right? The higher the answer, the more will be the source. What will be the solution for that? Infinite everywhere, right? That's all. Net value of the source. Okay, so locally you may have some source which can be larger. Plus, okay, so say it again. Minus 100 plus 5t. Okay, so in that case, SC equals, so this is an example that is suggested, which is minus 100 plus 5t. Yeah, so in this cases, okay, in this cases, the argument is that, okay, the source has a sink term, right? But we have a 5t that is kind of a source, right? So with this we still get a bounded solution, right, not an infinite solution, but then the problem is that diagonal dominance is not satisfied. Like, how do I deal with this thing, right? So to deal with these kind of problems, we have something known as relaxation, which is kind of artificially changing the diagonal dominance. Okay, we will come to that little later. Okay, but you would not get a problem where it will be just 5t. You don't have a kind of a positive feedback loop physically possible. Okay, but as he said, you can have a different model, or you can have a transient model where you may have, let's say, the source is switched on for some time and then it kind of switches off before it reaches infinite, right? That is possible. If that is there for these kind of problems, we would have something known as relaxation, under relaxation, where we kind of change the coefficient of AP, coefficient of VP, which is AP by certain amounts, okay, to deal with the diagonal dominance issues. Okay, yes. Say it again. T star and T for the same. So is the T star and T for the neighboring cell temperatures or for the same? They are for the same cell, right? Essentially we are talking about TP and talking about TP star. Both are evaluated for the same cell P. Okay, the previous iteration value and the current value that you want to calculate. Other questions? Okay, so we saw all these things. Now let us kind of plot all these 1, 2, 3, 4, the 4 examples we have for the source term linearization on an ST relation. Okay, so that is basically we have the source term on the y axis and temperature on the x axis. Let's say the blue curve is my model, that is S, this is essentially what was the model that is given, 4 minus 5t cube, right, that is the model I have, and let us say this is dp star, okay, that is dp star, and what would the first model, the Taylor series expansion, produce a line that looks like? It should be tangent to the curve, right, because it is a ds dt times t minus dp star square, so it would be a tangent. So, if I use this curve, okay, so this is my first model, right, which has minus 15 as the slope. Now, anything if on this curve, if you have lines that have a positive slope, right, if you have a line that is like this, what does these indicate? These indicate basically a positive feedback loop as such, right. So, these are all has a, they violate your SB less than or equal to 0 rule, right. We said it SP has to be less than or equal to 0. If you have a positive slope, they all have plus, right, SC is a positive value. So, we will not talk about them at the moment, okay. Now, what is the other one we had? Other one we had was the lazy person's approach, which is SC is just 4 minus 5 TP star cube. So, that is essentially constant, right, the slope is 0. So, this is your second model, right, where it is just a constant value. What are the other two models we had? The third one is an equation for minus 5 t star square is what is the slope. So, that is less steeper than this, right. That means how does that look? That will look between 1 and 2, isn't it? That will be somewhere between 1 and 2. So, that would be this model. This is your equation 3, right. This all, and then how does the fourth one look like? Fourth one has minus 25 TP star square, right. This is the slope. So, how does the last one look like? Correct one, I would use the black. It would go like this, right, larger than this. So, this is your fourth one, okay. So, of course, you can draw as many as you want on this graph, but the correct one, the recommended one is the first one, that is based on the Taylor series expansion, okay. Now, okay, we will come back to this question of, well, we have arbitrarily changed the source by using Taylor series expansion. Now, is that correct? To answer that, we will look at the expansion we have, S equals S star plus ds dt or partial S partial t star times t minus t star, okay. So, if we consider any cell, this would be Tp minus Tp star times ds dt star. Now, if you attain convergence, what will be the difference between, what will be the values of Tp and Tp star? At convergence, 0, right. Essentially, the difference would be of the order of epsilon, right, very small. Essentially, Tp equals Tp star at convergence, right, by the time we reach convergence. Then what will be S and S star would be? Will be the same, right. Essentially, it will be the same. That means we are recovering the same source term that is given in the problem, okay. So, the correct source term is recovered, okay, at convergence. Now, what about the other models we have seen? Would they also, let us say we have used this 2, 3, 4 or something and then found a solution in the end, would they also satisfy, that will also model the correct source term or not? It will, right, because the slope does not matter anymore, because we are multiplying with Tp minus Tp star. If they reach a convergence value, then the slope would not matter, right, isn't it? So, that those are all also, if they converge, the value you would get would be correct value, right. Only thing is that the solver might struggle to kind of converge, that is the only issue. Fine. Questions till now? Yeah. Yes. Okay, yeah. So, essentially the question is we are neglecting the higher order terms, right. There will be some error, right. How do we quantify? So, there will be certain order of accuracy for modeling this source, okay. We will show that as second order accuracy, which would be the same as the other spatial discretization accuracy, okay. We are not considering that because why? A linear model. If you consider, then it will be same as what is given, right. You will have the t square term and then you will get the t cube term and then it will be the same as what the model that is given as, okay. Other questions? No, clear? Okay. So then there is one more thing that we have to discuss, that is basically under relaxation, because now that we have touched upon it. But before we do that, I want to go back and kind of answer this question that somebody had yesterday. Can we solve an example problem of the TDMA and the line by line TDMA? Okay. So we will just quickly go through that. Okay, probably do a 1D problem for calculating the TDMA, and then we will probably look at a 2-dimensional problem as well. Okay. I think this is somebody asked yesterday. I think you asked this question yesterday, right? Okay. So shall we do that, and then we will come back to discussion on under relaxation after we finish this. Fine. So let us look at an example problem. This is very straightforward. So example problem is, we have, let's say, the boundaries. Let's say we have 1D steady diffusion. Let's take source equal to 0 for the sake of simplicity, and we have 3 cells. Okay. So delta x let us take as 1 meter. Okay. And then the temperatures would be 100 degrees Celsius and 400 degrees Celsius. Okay. And then I have 3 cells, which is 1, 2 and 3. Source is 0, and then let us take gamma or K as 1 watt per meter Kelvin. Okay. Essentially it will just easy for us, it will be easy if we take numbers like this, and then let us also take area as 1 meter square. Okay. That is the area of the faces. So 1D problem anyway. Fine. So what do we do? What is the first step? You generate the discrete equations, right? Discrete equations, and if you are using a Gauss-Seidel, you would again guess values for 2 and 3, T2 and T3, and calculate the value of T1, go to T2 and so on. That you are familiar with, right? Gauss-Seidel. Now let us look at how does this work in a TDMA. Okay. So we are applying a direct method, but first we need the equations. So what would be the equations? Can you tell me what would be, if I take cell 1, what would be A east? A east is, okay, that would be gamma east, A east by del x E, right? So gamma is 1, A is 1, del x is 1, all of them are 1, A east is 1. Okay. What would be A west? We do not have A west, we have something known as A, if we call this as A and if we call this as B, we have something known as AA, right? This is our A west. What would this be? Gamma west, A west upon del x B or del x A, right? What will this be? 2, because this is gamma is 1, A is 1 and delta x A is half, right? So this is 2. Okay. Then source is 0. Then what would be the final equation? What will go into AP? A east, right? A west is not there, but would AA go into AP? Yes, it will go, because the boundary condition given is a Dirichlet boundary condition, it will go into AP. So what will be AP? 3, okay, 3, because SP is 0, 3 times T1 equals, what would be the equation? AE times what? T2, that means 1 times T2, right, that is AE times T2 plus 2 times 100, right. Essentially this is AW times TW, TW is nothing but TA. So that is what we have written here is A times TA, right. That is all. Do you all agree with this or no? Agree? Easy? Do you already see the diagonal dominance? 3, okay, fine. Then let us write the other equation. Now it is very easy, just by looking at it you can tell me what would be the equation for cell 2. Yeah, so for cell 2, would you get this kind of term like 2? No, because you do not have boundaries, you have 1 and 3. So east and west would come out to be 1 each. So essentially for cell 2, A east equals A west equals 1, and what would be AP? 2. That means what would be the equation for cell 2? 2 times T2 equals T1 plus T3 plus 0, right. Source is not there, boundary condition is not there, nothing is there. Okay. What about cell 3? Cell 3 would have A west as how much? A west is 1, A east, which is known as A B, is 2, right, because we have gamma east A east by del x B, right. This is 1/2, right, because we only have half the cell here, right. So, this is del x B equals 0.5. So, as a result A B will come out to be 2. Then what will be the equation for a cell 3? 3 times T 3, because A P would be A west plus A B, right. 3 times T 3 equals 1 times T 2 plus 2 times, that is A B times T B, that is 400. So, this is nothing but T 3 T 3 equals T 2 plus 800, right. So, essentially we obtained all the 3 equations. I would just write down the equations. Equations are 3 T 1 equals T 2 plus how much? 200. Okay. Then 2 T 2 equals T 1 plus T 3 plus 0, nothing else here. Okay. What about the third one? 3 T 3 equals T 2 plus 800, fine. So, we have these 3 equations. Now, we will apply TDMA. Okay. So, we apply TDMA. So, in our TDMA we had some A, B, C, D, right. So, let me write down those things, otherwise it will be difficult. So, we have AI TI equals BI TI plus 1, right. Was it BI together with the east coefficient TI plus 1 plus CI TI minus 1 plus DI, right. This is what we had, and we also had P1 equals B1 by A1 and Q1 equals D1 by A1, right. That is what we had. So, for then what would be, so we are essentially applying TDMA in the positive x direction. What would be P1? P1 would be for cell 1, right, that is B1 by A1. What is B? B is 1, right, because Ti plus 1 is T east. B is 1. So, this is 1 upon what is A1? 3, right, because A is this guy, right, that is okay. What about Q1? D1 by A1, what is D1? 200, A1 is 3, okay. So, this would be 200 upon 3, right, that is what we have. Okay, P1, Q1 are known. What is the next step in TDMA? Calculate Pi Qi, right, essentially. So, what is the relation? Pi equals Bi upon Ai minus Ci Pi minus 1, is that correct? Okay, and then what is Qi? Qi equals Di plus Ci Qi minus 1 upon Ai minus Ci Pi minus 1, is that correct? Di plus, yeah, can you look it up from your notes and confirm? Yeah, that is correct, okay. Then what is, so we are now at cell 2. So, what is P2? P2 is B2 by A2 minus C2 P1. So, what is B2? B is the coefficient of what for cell 2? Of T3, right. So, that is 1, isn't it, because BITA plus 1. So, this is 1 upon how much is A2? A2 is the coefficient of T2. So, this is 2. This is 2 minus how much is C2? C2 1, right, because it is coefficient of Ti minus 1. So, this is 1 times how much is P1? 1/3, okay. So, this is how much? 3/5, is it? 2 minus 1/3, 6, 5, 3/5, is that correct? Okay. Then what about Q2? D2 plus C2 Q1 upon A2 minus C2 P1, right. How much is D2? D2 for cell 2, how much is it? 0, because we do not have a, so this is one catch, okay. We will come to this when we do 2D. So, in 1D you have 0. So, this is 0 plus what is C2? C2 is 1, okay, times what is Q1? 200 upon 3 upon A2 minus C2 P1 is again how much? 5/3, right? That is 5/3. So, this is 40, is it 40? Oh, sorry, yeah, 40, 200 by 3 by 5 by 3. Okay, so this is Q2, fine. All right, now what about next values? P3, B3 by A3 minus C3 P2, how much is B3? B3, so B is the coefficient of Ti plus 1. So, we are looking at 3, T3, what would be coefficient of T4? 0, right? Do you remember we said Pn equals Bn equals 0, right? We cut off the links to the outer cell. So, this is how much? 0, right? Because B3 is 0. What about Q3? Q3 is D3 plus C3 Q2 upon A3 minus C3 P2. How much is D3? D3 is 800, okay. So, this is 800 plus C3. C is the coefficient of Ti minus 1, right. That means how much? 1, okay. So, this is 1 times how much is Q2? 40 upon A3 minus C3 P2. How much was A3? 3. C3 1. How much was P2? 3/5. Okay. So, what will be this value? 840 upon 12 by 5. This is 12 by 5. How much would this be? 350. 1270s. Okay. So, we have Q3 is 350. So, Q3 is 350. Now, what is the next step? T3 is how much? Q3. So, T3 is 350 degree Celsius. So, we already started back substitution, right. Then what do you use? You use the relation Ti equals Pi Ti plus 1 plus Qi and calculate all the other values, right. You go back substitution. So, what is T2? P2 T3 plus Q2. How much is P2? 3/5, okay. 3/5. T3 just we got it as 350 plus Q2 40, okay. So, this is 40. So, we have 70. So, this is 250, right. 370 is 210 plus 40. This is 250 degrees Celsius. Okay. What about the last one? T1 equals P1 T2 plus Q1, right. How much was P1? How much? 5/3, okay. 5/3 of 2, 1/3, okay. So, this is 1/3, 1/3 of 250 plus how much is Q1? 200. Is P1 correct? 200 by 3, okay, 200 by 3, that makes sense, okay. So, we have 450 by 3, this is 150 degrees Celsius, okay, that is T1. So, essentially we have 100 and 400 as boundary conditions, we got 150, 250 and 350, right, from our TDMA. That is just like one go, okay. Now, is this correct? We can of course solve it analytically, but if you do it in the exam, unless it is asked, you do not get points, okay. So, we use d by dx of k dt dx to verify, plus s is 0 equals 0. Then what would be the solution for this? Integrated 2 times, what will be t? K dt dx equals some constant and t equals C1 by k times x plus C2, right. That is what we get. And what would be your C1 and C2? X equals 0, what is the temperature given? 100 degrees Celsius. X equals 3 meters, what was TB? 400 degrees Celsius. If you plug it in, x equals 0 gives you C2 equals 100, x equals 3 gives you 400 equals C1 times 3 upon 1 plus 100. So, C1 is also equal to 400 minus 100, 300 by 3, this is also 100, okay. It is also 100. Then what is the final answer? T equals 100x plus 100. So, 100 times x plus 1, right. That is 100x plus 100, okay. So, what is for cell 2, what is x? 1.5, right, or for cell 1, what is x? 0.5, right. So, then what we get is T1 equals 150, cell 2, xp is 1.5, right. It is halfway, isn't it? So, go back, oh, I've done a lot. So, this is how much? 0.5, 1.5 and 2.5, multiply, so 2.5 would give you how much? 250 degrees Celsius. Cell 3 would give you xp is 2.5, T3 is how much? 350 degrees Celsius, okay, fine. Now, we just have to write a code for this, same, it is very straightforward, fine, okay, happy. Now, we will do a 2D problem as well, fine, okay. Questions on this? No? You are able to follow, right? Able to think through, okay. Let us move on with a 2D problem, again a very simple problem. So, essentially I want to demonstrate how do you do the line by line method, okay, because we said we will do TDMA in the y direction and x direction we would do some kind of a Gauss-Seidel kind of thing. Let us look at a 2D problem. So, example 2, again let us consider a domain, 2D domain. We have only 4 cells. Let us call cells as I will call it as 1, 2, 3, 4, okay, that probably would be easy, okay. And then of course, we have boundaries, these are the boundaries of these faces, okay. Now, the boundary condition on this side, let us call it as T1 as 100 degrees Celsius, let us call TA. So, for the entire face, okay, is 100 degrees Celsius. On this side, we have TB equals 200 degrees Celsius and bottom is T3 equals 300 degrees Celsius and T4 is 400 degrees Celsius, fine. So, essentially we call it as ABCD, no. So, let me change it, I call it TA, TB, TC, TD, okay. So, now again if you assume source equals 0, K or gamma equals 1 watt per meter Kelvin, and what other values we need? We need delta x equals delta y equals 1 meter, okay. Everything is, we are setting it as 1. Then what is the problem here? Calculate T1, T2, T3, T4, okay. So, essentially calculate T1 to T4, okay, using finite volume method, okay, and using line by line TDMA. We have to calculate, we will just do like one iteration of the sweep, okay, or maybe not even one, okay, just one solid solution, fine. Looks okay, this problem. Okay, now you have to help me set up the discrete equations, okay, very easy, because now that you have done the 1D, you will easily be able to tell what are the coefficients. So, let us say cell 1, what will be A east for cell 1? Okay, area vectors would again be same as delta y, so we do not have to worry. What will be A east? Gamma east delta y by del x e for cell 1, right. What would this come out to be? 1, okay, very good. What about A north? Gamma north delta x by del y north, what would this come out to be? 1, okay, very nice. What about A west? 2, so this is gamma west delta y by del x b would become half, right, because it is only this much. So, this is only 0.5, as a result this will be 2, and if you apply the same logic, what would be A south? 2, because A west and A south are for these two phase centroids. So, this will also come out to be value of 2, okay, very good, very nice. Now, what will be the final equation? AP will have contributions from A east, A west, A east, A north, and these two are actually A west and A south are what? Are kind of boundaries, right. So, this is actually AB1 and this is some kind of AB2, right. These are two boundaries, one west and one south. So, these coefficients will go into two places. One is to the contribution of AP, the other one is when they are multiplied with the corresponding temperature, that will go as a B term, source term, right, B term on the right hand side. So, what will be the final equation for cell 1? 4 or 6? 6, right, because you have 1 plus 1 plus 2 plus 2, right. So, this is 6 times T1 equals what neighbors will be there? T2 and T4, okay. So, that is how much will be coefficients for T2? 1 times T2 for 4, 1 times T4 plus what else will you have? 2 times 100 plus 2 times 300, right, that is basically your these two. So, that is 2 times 100 plus 2 times 300, okay. So, that is 6T1 equals T2 plus T4 plus how much? 800, okay, fine, that is your equation for cell 1. Now, okay, now you would directly tell me what would be the equations for cell 2, cell 3, cell 4 without actually calculating them, okay. So, that is the beauty. Now, what is the equation for cell 2? 6T2 equals what will be the neighbors? T1 and T3. So, this is T1 plus T3 plus how much will be the boundary terms? 2 into 400, that would be 800, and 2 into 100, that will be 1000, okay. So, this will be 1000, fine. And then what is the equation for cell 3? They are all symmetric, right, all the cells share 2 faces. So, because of that you would get 2 interior coefficients which is 1 1 and 2 boundary coefficients which is 2 2, right. As a result they all add up to 6. So, this will be 6T3 equals what are the neighbors for cell 3? Cell 3 has 2 and 4, right. So, this will be T2 plus T4 plus how much will be the boundary values? 400 into 2 plus 200 into 2, that is how much? 1200, okay. Then for the final cell 6T4 equals what are the neighbors for T4? 1 and 3. So, that is T1 plus T3 plus what will be the boundary value? 1000, that is because 200 into 2 plus 300 into 2, right, that is 500 into 2, that is 1000, okay, fine. So, we got all the 4 equations. Questions on this part? Clear, easy, right. Now, of course, if there is a source term you have to be careful, you have to add the source term, and if there is a dependency on x or t, then you have to be careful, okay, fine. Okay, now of course, we have these equations. What we have to do is we have to apply TDMA in the y direction, that is for cell 1 and 2 we have to apply TDMA, and then you would use the guess values for T4 and T3 while you collect coefficients for these things, right, that is what we would do. And where would the coefficients, where would these T3, T star, T4 star go while writing these equations for TDMA? They will go into the constant on the right hand side on the boundaries, okay. So, we are kind of out of time. So, I will stop here. Tomorrow if you can let me write these equations again, we will do a TDMA loop and then move on with under relaxation and other things, fine, okay.